welcome to the second episode of Topology for the series Gravitation. So we have reached closed subsets. We have talked about open subsets in the last video, and now we are going to introduce closed subsets in topology. And there is a misunderstanding about closed subsets and open subsets, which I'm going to point out. And when we are talking about closed subsets and open subsets, we are talking about a more general concept from open subset and closed subsets in mathematical analysis, or as we know in the space, in the Euclidean space. So this is more generalized than that, and there are some differences, and I'm going to show them to you. So by definition, if X is a topological space, a subset F of X is said to be closed if its complement is open, and which complement means this one right here, X subtracted by F. And this is a subtraction in the sense of sets. So this is the definition of a closed subset or a closed set. And with this definition right here, we can rephrase the condition of X to be a topological space in the following way. So I'm going to show where did this 3 came from, and these conditions are now expressed in the terms of closed sets. The first term, if you can remember, was that X and the empty set are open sets, or the sets that are in our curly T. So now we have that X and the empty set are closed sets. Where did this come from? Well, it's quite easy actually. The complement of X will be the empty set, and the complement of empty set will be the whole X. So these are open sets. So if X and empty set are closed sets, then this means that empty and X are open sets. So that's how they are equal statements to express the first condition. The second one is that any union of finitely many closed subset of X is a closed subset of X. Well, if you remember, this and this was different in our conditions, which was expressed in the terms of open sets. This was intersection and this was open. Okay, and how did we derive this? Is by De Morgan's law. I mean, intersection of, say, U1 and U2. If we take a complement of that, we get U1C union U2 complement. And that's why these two are equal. And we have the same thing for the third one. Any intersection of arbitrarily many closed subset of X is a closed subset of X. Again, you do the De Morgan thing on open sets, you get this. So let's go see some examples of closed sets. And here I'm going to show you that misunderstanding that people may have in closed set and subsets, in closed sets and open sets. And here we go. let's suppose that our topological space is the interval 0 to 1, and this is a Euclidean topology. Now, a thing to mention is that this X itself is actually open. Okay, and why is it open? Because this is a topology and X needs to be in our topology, so it's open. And X is also closed. But if you're thinking about this only in the terms of math analysis, you may think that this is a closed set, but you'll have to pay attention that this is all of our space. Okay, it's not a subset of our space, it's the whole space. So in the next example, we have X equal to R, set of real numbers, and we want to see if this set is open or closed. And again, with Euclidean metric, and well, this is a closed set because R subtracted by this gives us a open set, and so this is open, but you have to pay attention that our space is the set of all real numbers. As you can see, these two are same, but the space we are talking about is different. So this is closed and not open in this space, but this is both closed and open. Then we have the Y, an arbitrary subset of our set of X. Then this is closed. Why is this closed? Topology is discrete topology. I have to say this, that X equals to discrete topology, and we are taking a subset, and this is closed the same way that in a discrete topology everything is open. So the one thing you need to remember is that closed does not mean not open. Okay, I mean, these two things are not in contradiction with each other. They're just two different properties of a set, and a set can be both closed and open, or can be neither of them. So do not mistake not closed as open or not open as closed. And that's it. We have some definitions. These definitions helps us to understand the properties of different sets better. The first one is the closure of A, which we show it with a bar, and it's defined like this. It's the intersection of all B's, which are subsets of X, and B are closed, with this condition that A is a subset of B. So this is a closure of A. And then there is interior of A. We show it with int A, or with A with a little circle up above it. And this is defined as union of B's, which B's are subsets of X, and B's are open, and B's are also a subset of A. So what are these actually? I mean, if I want to visualize this, the closure of A looks like this. Let's suppose that this is just a visualization. I mean, this is not definitely correct. It just gives you an idea of what a closure of A is. So let's suppose that this is our set A. Now, what this closure means is it takes the intersection of all things that A is contained in and B is closed. Like if this is B, if this is some B, then, or this is some B, and these are all closed subsets of X, then this is the intersection of all of them until it reaches A. So as you can see, there is nothing left that from the boundary of A, which is not covered by this B. That's just a visualization. Another way we can interpret this is that A bar contains all of its boundary points or limit points, and we are going to get to that. So this intersection will be something like this. As you can see, I have covered all of A and also a boundary of it. So that is what A bar is. The interior of A, or as we show it, int A, is something opposite of that. Like if we have this set A, then I'm taking unions of all B's which are contained in A until I reach a point which my sets are open still, but also they're still a subset of A. So this will be those sets. As you can see, I'm trying to not cover the boundary, and that is what int A is. So I mean, these are just some visualization. I mean, in some other space this may even be false, but we usually work with Euclidean space, and this is true in Euclidean space. So yeah, that's it. And then we have the exterior of A, which is X subtracted by A bar. Again, if I want to show that this is, let's suppose that this is A, then exterior of A will be all of the points that are outside of A and even the boundary of A. Okay, I'm excluding also the boundary. So this is a visualization of exterior of A. Then we have the boundary of A, which is defined to be X subtracted by the union of interior of A and exterior of A, which will be this thing right here, this circle. This is the boundary of A. And yeah, that's it. Then we have some propositions. Sometimes to work with subsets, we need some equivalence, some equivalent properties which describes sets in other words. For example, a point in int A, a point is an int interior of A if and only if it has a neighborhood contained in A. These are our propositions. You can prove them. I'm just going to give you a hint. Why is that true? Let's suppose that a point is in interior of A, Then by definition, let's see what was the interior of A. If a point is in the interior of A, then it is in some B, and since B is open, then it has a neighborhood contained in A. I mean, that's how you should go for the proof. The same thing goes for B. It's pretty similar. I mean, this is just a complement space. Then we have a point is in boundary of A if and only if every neighborhood of it contains both a point of A and a point of X subtracted by A. And that is just, let's say if we have a point here, then for every neighborhood around it, you can see that it does intersect the A itself and the exterior of A. So yeah. Then we have a point is in A bar if and only if every neighborhood of it contains a point of A. This is actually quite hard. I couldn't get it straightly, but with a bit of algebra, I think you can do it. And that is just that is just equivalent from this. This is just the equivalent form of this. And then we have interior of A and exterior of A are open in X, while A bar and boundary of A are closed in X. Well, this is really simple from this definition right here. Well, A bar, I mean, we have to interior and exterior of A are, interior of A is obviously open because it is the union of open sets, and so exterior of A is just the complement of it's just the complement of X minus A bar, which I will say why this is a closed set. So this is closed, then this is open, excuse me, this is open. So why A bar is closed? Well, because it's just the intersection of closed sets, and intersection of closed sets are closed. And this was X subtracted by int A union X A. So these two are open, so their union is open. So if we subtract this from X, then we get a closed set. Then there is these equivalent propositions. These things are all equivalent to each other. You can use one instead of other. So if A is open, then A equals int of A. This is just derived from the definition. A was the union of all open sets. So then if A is open, then A should be equal to the greatest open subset, which would be the A itself. So yeah, this is really trivial. A contains none of its boundary points. Then again, we use the fact that every point in A, if we have a neighborhood around the point, it doesn't cut the boundary, and yeah, that's the job. Every point of A has a neighborhood contained in A. Again, since A is open, then, or you can use this, it's a collection of open sets. So yeah. Now these are all you can do the same for these closed ones. They're just slightly different. So you can go through all of these separately and prove them for yourself. Then we have a definition. our definition is given a topological space X, we say P member of X is a limit point of A if every neighborhood of P contains a point of A other than P. If I want to do an example, is take the interval 0 to 1, but 1 is in our set, then 1 is a limit point, and 0 is also a limit point. And interestingly enough, all of the points in between are also a limit point. But there are some difference. I mean, these limit points are also an interior point, but these limit points are not in our set, and these limit points are in our set, but I mean from one side. Yeah, and remember, we are in the space of real numbers with Euclidean topology. So a point P is called isolated if there exists a neighborhood Ux intersection at with A, then it should be equal to the set P. Well, for this, I can give you this example. I mean, take this 0 to 1, then there's a point 2, and then there is 3 to 4. Well, a 2 is an isolated point. As you can see, around this, there is only one point which intersects with our set, which is 2 itself. Now, there is another definition called dense. Subset of A of X is called dense in X if the A bar equals the whole X. And for this, I can give you an example of rational numbers in set of real numbers. As you can, by definition, you can say that real numbers are actually the limit points of Q. So yeah, these are dense since A bar is limit points of A union it with A itself. So yeah, that's it. And this was just some properties of subsets of sets in topological spaces. And in the next videos, we are going through some other concepts in topology. Thank you for watching. Do not forget to subscribe, and bye-bye.